Okay, let's start. Deadline IO scheduler. I'm gonna start right at this part again because I want to be at a place where I can remember what was going on. Okay, the deadline IO scheduler. Am I recording? Okay, there we go. The deadline IO scheduler sought to prevent the starvation caused by the Linus elevator. In the interest of minimizing seeks, heavy disk I/O operations to one area of the disk can indefinitely starve request operations to another part of the disk. Indeed, a stream of requests to the same area of the disk can result in other far-off requests never being serviced. This starvation is unfair. Worse, the general issue of request starvation introduces a specific instance of the problem known as write-starving reads. Write operations can usually be committed to disk whenever the kernel gets around to them. So again, one thing to remember is that disk writes to the file system are always asynchronous and don't happen immediately, versus reads are almost always blocking and synchronous. So again, so whenever the kernel gets around to them, entirely asynchronous with respect to the submitting application. Read operations are quite different. Normally, when an application submits a read request, the application blocks until the request is fulfilled. That is, a read request occurs synchronously with respect to the submitting application. Although system response is largely unaffected by write latency, or the time required to commit a write request, read latency, the time required to commit a read request, is important because it is blocking. Write latency has little bearing on application performance because it happens at any other time. It's asynchronous. So it's not really dependent on what you're trying to achieve at that moment. But an application must wait, twiddling its thumbs for the completion of the read request because it's synchronous. Consequently, read latency is important to the performance of the system. Compounding the problem, read requests tend to be dependent on each other. For example, consider the reading of a large number of files. Each read occurs in small, buffered chunks. The application does not start reading the next chunk, or the next file for that matter, until the previous chunk is read from disk and returned to the application. Worse, both read and write operations require the reading of various metadata, such as inodes. Reading these blocks off the disk further serializes I/O. Consequently, if each read request is individually starved, the total delay to such applications compounds and can grow enormous. Recognizing that the asynchrony and interdependency of read requests result in a much stronger bearing of read latency on the performance of the system, the deadline I/O scheduler implements several features to ensure that read request starvation in general and read starvation in specific is minimized. Okay? So, note that reducing request starvation comes at the cost of global throughput. Even the Linus elevator makes this compromise, albeit in a much milder manner. The Linus elevator could provide better overall throughput, that means the number of requests being serviced in some period of time, via a greater minimization of seeks if it always inserted requests into the queue sector-wise and never checked for old requests and reverted to insertion at the tail of the queue. Although minimizing seeks is important, indefinite starvation is not good either. So that means a request could just keep getting pushed to the back until it is never handled because some other thing is always a higher priority. So then that's the Linus elevator, right? But then the deadline IO scheduler therefore works harder to limit starvation while still providing a good global throughput. Make no mistake, it is a tough act to provide request fairness, yet maximize global throughput. In the deadline IO scheduler, each request is associated with an expiration time. By default, the expiration time is 500 milliseconds in the future for read requests and 5 seconds in the future for write requests, mainly because writes tend to be slower and also because they are asynchronous. The deadline I/O scheduler operates similar to the Linus elevator in that it maintains a request queue sorted by physical location on disk. Okay? It calls this queue the sorted queue. When a new request is submitted to the sorted queue, the deadline I/O scheduler performs merging and insertion like the Linus elevator. The deadline I/O scheduler also, however, inserts the request into the second queue that depends on the type of request. Read requests are sorted into a special read FIFO queue, and write requests are inserted into a special write FIFO queue. Although the normal queue is sorted by on-disk sector, these queues are kept FIFO. Effectively, they are sorted by time. Consequently, new requests are always added to the tail of the queue. Under normal operation, the deadline I/O scheduler pulls requests from the head of the sorted queue into the dispatch queue. The dispatch queue is then fed to the disk drive. This results in minimal seeks. Okay? If the request at the head of either the write FIFO queue or the read FIFO queue expires, that is, if the current time becomes greater than the expiration time associated with the request, 500 milliseconds in the future for reads, 5 seconds for the future for writes. Okay, the deadline I/O scheduler then begins servicing requests from the FIFO queue. In this manner, the deadline I/O scheduler attempts to ensure that no request is outstanding longer than its expiration time. Okay, so again, three different queues. Okay, so note that the deadline I/O scheduler does not make any strict guarantees over the request latency. It is capable, however, of generally committing requests on or before their expiration. Okay, this prevents request starvation because read requests are given a substantially smaller expiration value than write requests. The deadline I/O scheduler also works to ensure that write requests do not starve read requests. This preference towards read requests provides minimized read latency. The deadline I/O scheduler lives in block deadline IOsketch.c. Okay. So that's deadline. Now it's anticipatory I/O scheduler. Although the deadline I/O scheduler does a great job minimizing read latency, it does so at the expense of global throughput. Consider a system undergoing heavy write activity. Every time a read request is submitted, the I/O scheduler quickly rushes to handle the read request. This results in the disk seeking over to where the read is, performing the read operation, and then seeking back to continue the ongoing write operation, repeating this little charade for each read request. The preference toward read requests is a good thing, but the resulting pair of seeks, one to the location of the read request, another back going to the ongoing write, is detrimental to global disk throughput because you're constantly going back and forth seeking. And this is back then when hard drives were still quite common. The anticipatory I/O scheduler aims to continue to provide excellent read latency, but also provides excellent global throughput. First, the anticipatory I/O scheduler starts with the deadline I/O scheduler at its base, as we have read before. Therefore, it is not entirely different. The anticipatory I/O scheduler implements 3 queues plus a dispatch queue and expirations for each request. Just like the deadline I/O scheduler, the major change is the addition of anticipation heuristic. The anticipatory I/O scheduler attempts to minimize the seek storm that accompanies read requests issued during other disk I/O activity. When a read request is issued, it is handled as usual within its usual expiration period. After the request is submitted, however, the anticipatory I/O scheduler does not immediately seek back and return to handling other requests. Instead, it does absolutely nothing for a few milliseconds, just in case, right? Just to wait, see if there's anything close by that's coming. The actual value is configurable. By default, it is 6 milliseconds. Okay. So wait for at least 6 milliseconds by default. In those few milliseconds, there is a good chance that the application will submit another read request. Any requests issued to an adjacent area of the disk are immediately handled. After the waiting period elapses, the anticipatory I/O scheduler seeks back to where it left off and continues handling the previous requests. It is important to note that the few milliseconds spent in anticipation for more requests are well worth it if they minimize even a modest percentage of the back and forth seeking that results from servicing of read requests during other heavy requests. If an adjacent I/O request is issued within the waiting period, the I/O scheduler just saved a pair of seeks. As more and more reads are issued to the same area of disk, many more seeks are prevented. Of course, if no activity occurs within the waiting period, the anticipatory I/O scheduler loses and a few milliseconds are wasted. The key to reaping maximum benefit from the anticipatory I/O scheduler is correctly anticipating the actions of applications and file systems. This is done via a set of statistics and associated heuristics. The anticipatory I/O scheduler keeps track of the per-process statistics pertaining to block I/O habits in hopes of correctly anticipating the actions of applications. I wonder that's how that's going to be now with like AI. Like, I wonder if we can make better file system scheduling with that. With a sufficiently high percentage of correct anticipations, the anticipatory I/O scheduler can greatly reduce the penalty of seeking to service read requests, while still providing the attention to such requests that the system response requires. This enables the anticipatory I/O scheduler to minimize the read latency while also minimizing the number of durations of seeks. This results in low system latency and high system throughput. The anticipatory I/O scheduler lives in the file block anticipatory as ioschedule.c in the kernel source tree. It performs well across most workloads. It is ideal for servers, although it performs poorly on certain uncommon but critical workloads involving seek-happy databases. Okay, so we get to the completely fair queuing I/O scheduler. The complete fair queuing CFQ I/O scheduler is an I/O scheduler designed for specialized workloads, but that in practice actually provides good performance across multiple workloads. It is fundamentally different from the previous I/O schedulers that have been covered, however. Okay, so a lot of them have so far been sort of based off of each other as inspiration and just kind of like tacking on features on top. This one is going to be different. Okay, so let's read. The CFQ I/O scheduler assigns incoming I/O requests to specific queues based on the process originating the I/O request. For example, I/O requests from the process foo go in foo's queues, and I/O requests from the process bar goes in bar's queue. Within each queue, requests are coalesced with adjacent requests and insertion sorted. So insertion sort is the algorithm for this. The queues are thus kept sorted sector-wise as with the other I/O schedulers' queues. The difference with the CFQ I/O scheduler is that there is one queue for each process submitting I/O. The CFQ I/O scheduler then services the queues round robin, plucking a configurable number of requests, and by default that is 4, from each queue before continuing on to the next. This provides fairness at a per process level, assuring that each process receives a fair slice of the disk's bandwidth. The intended workload is multimedia, in which such a fair algorithm can guarantee that, for example, an audio player can always refill its audio buffers from disk in time. In practice, however, the CFQ I/O scheduler performs well in many scenarios. The complete fair queuing I/O scheduler lives in block/CFQ I/O schedule.c. It is recommended for desktop workloads, although it performs reasonably well in nearly all workloads without any pathological corner cases. It is now the default I/O scheduler in Linux. Okay, so the one I'm not sure we still use it, is the CFQ I/O scheduler. General purpose. Okay, so noop I/O scheduler. A fourth and final I/O scheduler is a no-op I/O scheduler, so named because it is basically a no-op. It does not do much. The no-op I/O scheduler does not perform sorting or any form of seek prevention whatsoever. In turn, it has no need to implement anything akin to the slick algorithms to minimize request latency that you saw in the previous three I/O schedulers. The no-op I/O scheduler does perform merging, however, as its lone chore. Okay. When a new request is submitted to the queue, it is coalesced with any adjacent requests. Other than this operation, the no-op I/O scheduler truly is a no-op, merely maintaining the request queue in near FIFO order from which the block device driver can pluck requests. The no-op I/O scheduler's lack of hard work is with reason. It is intended for block devices that are truly random access, such as flash memory cards. If a block device has little or no overhead associated with seeking, then there is no need for insertion sorting of incoming requests, and the no-op I/O scheduler is the ideal candidate. Oh, okay, so for like SSDs and things like that, because there's no point in trying to organize all your file system requests to kind of maximize the needle of your disk moving when you're just blasting electrons into an SSD. Okay, that makes a lot of sense. The no-op I/O scheduler lives in block no-op I/O schedule.c. It is intended only for random access devices, like SSDs. Okay, so I/O scheduler selection. You have now seen 4 different I/O schedulers in the 2.6 kernel. Each of these I/O schedulers can be enabled and built into the kernel. By default, block devices use the complete fair queuing I/O scheduler. This can be overridden via the boot time option elevator equals foo on the kernel command line, where foo is a valid and enabled I/O scheduler. See table 14.2. So it'll be elevator equals AS if you want anticipatory, CFQ if you want completely fair queuing, deadline for deadline, no-op for no-op. So for example, the kernel command line operation or option elevator equals AS would enable use of the anticipatory I/O scheduler for all block devices, overriding the default complete fair queuing scheduler. So in conclusion, in this chapter, we discussed the fundamentals of block devices, and we looked at the data structures used by the block I/O layer, the BIO representing in-flight I/O, the buffer head representing a block-to-page mapping, and the request structure representing a specific I/O request. We followed the I/O request on its brief but important life, culminating in the I/O scheduler. We discussed the dilemmas involved in scheduling I/O and went over the 4 I/O schedulers currently in the Linux kernel and the old Linux elevator from 2.4. Next up, we tackled the process address space. Okay, yet another chapter. Okay, chapter 15. We are pretty much, I think we're at this point almost 80% of the way there to finishing the book. Okay, the process address space. Chapter 12, memory management, looked at how the kernel manages physical memory. In addition to managing its own memory, the kernel also has to manage the memory of user space processes. This memory is called the process address space, which is the representation of memory given to each user space process on the system. So Linux is a virtual memory operating system, and thus the resource of memory is virtualized among the processes on the system, meaning that an individual process's view of memory is as if it alone has full access to the system's physical memory. More important, the address space of even a single process can be much larger than the physical memory. This chapter discusses how the kernel manages the process address space. Yep, virtual memory. Okay, so that also has to do with paging and all that stuff. So address spaces. Okay, so it's important to know this one. The process address space consists of the virtual memory addressable by a process and the addresses within the virtual memory that the process is allowed to use. Each process is given a flat 32 or 64-bit address space, with the size depending on the architecture. So the term flat denotes that the address space exists in a single range. For example, if you have a 32-bit address space, then we extend from the address 0 to 4,294,967,295. So that's the address range. You have from 0 to this 4 billion whatever number. So some operating systems provide segmented address space with addresses existing not in a single linear range, but instead in multiple segments. Modern virtual memory operating systems generally have a flat memory model and not a segmented one. Normally, this flat address space is unique to each process. A memory address in one process's address space is completely unrelated to that same memory address in another process's address space. Both processes can have different data at the same address in their respective address spaces. Okay? So that again, that goes back to the illusion of process thinking that it's the only one on the system. It has all the memory. What's happening internally is that the kernel is just switching back and forth between processes and also their view of memory. So you have two processes that can have, like, in the same address, different types of data, because that's all virtual. It's not really physical. In the real world, the mapping, the physical addresses are completely different. Okay, so alternatively, the processes can elect to share their address space with other processes. We know these processes as threads. Okay, so the memory address is a given value within the address space, such as 4021F000. This particular value identifies a specific byte. So one memory address is 1 byte in a process's 32-bit address space. Although a process can address up to 4 gigabytes of memory with that 32-bit address space, it doesn't have permission to access all of it. The interesting part of the address space is the intervals of memory addresses, such as 08048000 and 0804C000, that the process has permission to access. These intervals of legal addresses are called memory areas. The process, through the kernel, can dynamically add and remove memory areas to its address space. The process can access a memory address only in a valid memory area. Memory areas have associated permissions, such as readable, writable, and executable, and that associated process must respect it. If a process accesses a memory address that is not valid in the memory area, or if it accesses a valid area in an invalid manner, meaning that if you have a memory area that is supposed to be only readable but not writable, and you try to write to it, that's going to be a problem. That's going to be a seg fault. So the kernel kills the process with the dreaded segmentation fault message. So that's why, because these areas of memory have specific functionalities associated with them. You do the wrong thing on these areas, then your kernel doesn't really know what to do. It'll take the safest route and just kill the process. So memory areas can contain all sorts of goodies, such as a memory map of the executable files code, such as, we call that the text section. Some people call it the code section. A memory map of the executable files initialized global variables, called the data section. Sometimes we call that the global section. A memory map of the zero page, a page consisting of all zeros used for purposes such as this, containing uninitialized global variables, called the BSS section. A memory map of the zero page used for processes user space stack. I think zero page means like the first 4 kilobytes or 8 kilobytes of memory. So in that processes address space. So anyway, the stack, okay, do not confuse this with the processes kernel stack, which is separated and maintained by and used by the kernel. Any additional text data and BSS section for each shared library, such as the C library and dynamic linker, loaded into the process's address space. So any memory map files, any shared memory segments, and any anonymous memory mappings, such as those associated with malloc. Okay, so your memory map also has an area just like a heap. In this case, this is referring to heap, anonymous memory. So all valid addresses in the process address space exist in exactly one area. Memory areas do not overlap. As you can see, there is a separate memory area for each different chunk of memory in a running process. The stack, object code, global variables, mapped file, and so on. Okay. So the memory descriptor. The kernel represents a process's address space with a data structure called the memory descriptor. This structure contains all the information related to the process's address space. The memory descriptor is represented by the struct mmstruct type and defined in Linux/mmtypes.h. Let's look at the memory descriptor with comments added describing each field. Okay, so VM area struct type called mmap, which is the list of the memory areas. Okay, then we also have, what else we have? We have page global directory, don't know what that is. Primary usage counter, don't really know what that is. Oh, here, this is cool, this is useful. Here, you see the start code, end code, start data, end data, start BRK, BRK, start stack, and so on. These are all the starting addresses and ending addresses of these specific segments. So you see the start BRK, that's the start address of the heap, and BRK is the final address of the heap. Okay, and then we have the start of the arguments of your program. You know how like you can execute a program with your arguments? I think this is where it is in memory. Then your environment variables are here too. Environment start, environment end. Okay. Cool. I recognize this. This is better than the file system one. Okay, so the users field is the number of processes using this address space. For example, if two threads share this address space, users is equal to 2. The count field is the primary reference count for the struct. All users equate to one increment of count. Thus, in the previous example, count is only 1. If 9 threads share an address space, users would be 9. But again, count will only be 1. Only when users reaches 0, when all threads using an address space exit, is count decremented. When count finally reaches 0, there are no remaining references to this struct and is freed. So when the kernel operates on an address space and needs to bump its associated reference count, the kernel increments the count. Having two counters enables the kernel to differentiate between the main usage counter, count, and the number of processes using the address space, users. The mmap and mmap and mmrb fields are different data structures that contain the same thing, all the memory areas in this address space. The former stores them in a linked list, whereas the latter stores them in a red-black tree. A red-black tree is a type of binary tree. Like all binary trees, searching for a given element is O-log n operation. For further discussion on red-black trees, see lists and trees of memory areas later in this chapter. Although the kernel would normally avoid the extra baggage of using two data structures to organize the same data, the redundancy comes in handy here. The mmap data structure as a linked list allows for simple and efficient traversing of all elements. On the other hand, the mmrb data structures, such as the red-black tree, is more suitable for searching a given element. Memory areas are discussed in more details later in this chapter. The kernel isn't duplicating the struct structures, it's just containing the objects. Overlaying a linked list into a tree and using both to access the same set of data is sometimes called a threaded tree. Okay. All the struct structures are strung together in a doubly linked list via the list field. The initial element in the list is the init memory descriptor, which describes the address space of the init process. The list is protected from concurrent access via the list underscore lock, which is defined in kernel/fork.c. Okay. Allocating a memory descriptor. The memory descriptor associated with a given task is stored in the field of the task's process descriptor. The process descriptor is represented by the task structure defined in Linux schedule.h. So one of our first structures that we learned way back when. Thus, the current is the current process's memory descriptor. The copy function copies a parent's memory descriptor to its child during fork. The struct structure is allocated from the cache p slab cache via the allocate macro in kernel fork C. Normally, each process receives a unique struct and thus a unique process address space. Processes may elect to share the address spaces with their children by means of the clone VM flag to clone. The process is then called a thread. Okay, so whenever a process spawns a child process, and this process says, hey, you can share the same memory address space as me, meaning that you don't get your own, you just use mine. That's what we call a thread in Linux. Again, in some operating systems, thread and processes are two different constructs. It's just, and conceptually so too. It's just that in Linux, it's more or less the same, just that threads can share the process's memory. Data structure wise, they are the same. Okay, so recall from chapter 3, process management, that this is essentially the only difference. Yep, the only difference between normal processes and so-called threads in Linux. The Linux kernel does not otherwise differentiate between them. Threads are regular processes to the kernel that merely share certain resources. In the case that clone VM is specified, allocate is not called, and the process's field is set to point to the memory descriptor of its parent via this logic in copy Okay, so this thing here. All right, destroying a memory descriptor. When the process associated with a specific address space exits, the exit defined in the kernel exit C function is invoked. This function performs some housekeeping and updates some statistics. It then calls put, which decrements the memory descriptor's user's user counter. If the user count reaches 0, drop is called to decrement the count usage counter. Ooh, it's confusing. If that counter is finally 0, the free macro is invoked to return the struct to the cache p slab cache via cache free, because the memory descriptor does not have any users. Okay, so just decrement whenever we leave. whenever exit is called, I guess. And then when that decrement results in 0, then we legitimately free everything. Okay. So struct and kernel threads. Kernel threads do not have a process address space and therefore do not have an associated memory descriptor. Thus, the field of a kernel thread's process descriptor is null. This is the definition of a kernel thread: processes that have no user context. Kernel threads are processes that have no user context. That means they don't run under the process or any other process on behalf of that. So this lack of an address space is fine because kernel threads do not ever access any user space memory. Whose would they access in this case? Because kernel threads do not have any pages in user space. They do not deserve their own memory descriptor and page tables. Page tables are discussed later in this chapter. Despite this, kernel threads need some of the data, such as the page tables, or even to access kernel memory. To provide kernel threads the needed data without wasting memory on a memory descriptor and page tables, or wasting processor cycles to switch to a new address space whenever a kernel thread begins running, Kernel threads use the memory descriptor of whatever task ran previously. Whenever a process is scheduled, the process address space referenced by the process's field is loaded. The active field in the process descriptor is then updated to refer to the new address space. Kernel threads do not have an address space and is null. Therefore, when a kernel thread is scheduled, the kernel notices that the is null and keeps the previous process's address space loaded. Okay. Would that ever mean that the kernel thread could ever overwrite that specific process address space? Let's see. Good thinking though. The kernel then updates the active field of the kernel thread's process descriptor to refer to the previous process's memory descriptor. The kernel thread can then use the previous process's page tables as needed. Okay. Because kernel threads do not access user space memory, they make use of only the information in the address space pertaining to kernel memory, which is the name for all processes. Sounds a little dangerous to me. Virtual memory areas. The memory area structure VM area struct represents memory areas. It is defined in Linux/mm types.h. In the Linux kernel, memory areas are often called virtual memory areas or abbreviated as VMAs. The VM area struct structure describes a single memory area over a contiguous interval in a given address space. The kernel treats each memory area as a unique memory object. Each memory area possesses certain properties, such as permissions and a set of associated operations. In this manner, each VMA structure can represent different types of memory areas. For example, memory mapped files or the process's user space stack. This is similar to the object-oriented approach taken by the VFS layer. Here's the structure with comments adding to describe each field. Okay. This doesn't mean much to me yet. Okay. All right. So recall that each memory descriptor is associated with a unique interval in the process's address space. The VM start field is the lowest address in the interval. So that's the initial. Start is the lowest address in the interval. And the VM end field is the first byte after the highest address in the interval. So the last address is the highest address in value. That is, VM start is the inclusive start and VMM is the exclusive end of the memory interval. Oh wow, you figured they should have put this in a more obvious paragraph instead of inside a paragraph in a sentence. Okay, anyway, thus VMN minus VM start is the length in bytes of the memory area, which exists over the interval VM start inclusive and VMN exclusive. Intervals in different memory areas in the same address space cannot overlap. So the VMM field points to this VMA's associated struct. Note that each VMA is unique to the struct, which is it is associated. Therefore, even if two separate processes map the same file into their respective address spaces, each has a unique VM area struct to identify its unique memory area. Conversely, two threads that share an address space must also share the VM area struct structures therein. Let's see, we still have a little time. Okay, so VMA flags. The VM flags contains bit flags defined in Linux/mmh that specify the behavior of and provide information about the page contained in the memory area. Unlike permissions associated with the physical page, okay, the VMA flags specify behavior for which the kernel is responsible. Okay, not the hardware. Furthermore, the VM flags contain information that relates to each page in the memory area or the memory area as a whole, and not the specific individual pages. Oh, okay, bigger scope. Okay. So here are all the flags. I'm not going to list out all these flags again, or not going to say all of it. So I encourage the reader to just read it. Okay. So let's look at some of the more important, interesting flags in depth. Okay, see, I'm glad I didn't read it because you're gonna go over it anyway. Okay. The VM read, VM write, and VM exec flags specify the usual read, write, and execute permissions for the pages in this particular memory area. They are combined as needed to form the appropriate access permissions that a process assigning this VMA must respect. For example, the object code for a process might be mapped with VM read and VM exec, but not VM write. On the other hand, the data section from an executable object would be mapped VM read and VM write, but VM exec would make little sense. Meanwhile, a read-only memory mapped data file would be mapped with only VM read flag. The VM shared flag specifies whether the memory area contains a mapping that is shared among multiple processes. If the flag is set, it is intuitively called a shared mapping. If the flag is not set, only a single process can view this particular mapping, and it is called a private mapping. The VMIO flag specifies that this memory area is a mapping of a device's I/O space. This field is typically set by the device drivers when mmap is called on their I/O space. It specifies, among other things, that the memory area must not be included in any process's core dump. Okay? The VM reserved flag specifies that the memory region must not be swapped out, and it is also used by device driver mappings. Okay. The VM read or the VM seek read flag provides a hint to the kernel that the application is performing sequential, that is, linear and contiguous reads in this mapping. The kernel can then opt to increase the read ahead performed on the backing file. The vmran read flag specifies the exact opposite, that the application is performing relatively random, that is, not sequential, reads in this mapping. The kernel can then opt to decrease or altogether disable read ahead on the backing file. These flags are set via the madv system call with the madv sequential and madv random flags, respectively. Read ahead is the act of reading sequentially ahead of the requested data in hopes that the initial data will be needed soon. Such behavior is beneficial if applications are reading data sequentially. Okay. If data access patterns are random, however, read ahead is not affected. Okay. All right, I think that's a good stopping point for today.